Good almost afternoon, dear colleagues. Before to start, let me express my gratitude for the organizers to organizing this wonderful, well, as usual, wonderful conference, and also for giving me an opportunity to deliver a plenary talk. This is a great honor and also great responsibility for me because this is my first plenary talk. And before to start with the talk, I would like to dedicate this talk to the memory of Professor Nikolai Karapetovich Karapetyan's. I've never met him, and of course I'm not able to evaluate his achievements, but I've heard many times from elder colleagues that he was a gifted mathematician, a wonderful teacher, and a kind-hearted person. So, to the memory. Okay, let us start. I'm going to tell about the order properties of homogeneous polynomials, and let me start exactly from the definition of the notion of a homogeneous polynomial. Okay, we are working right now in vector lattices E and F. And we call a mapping P between E and F said to be S homogeneous polynomial or polynomial of degree S if for some multilinear operator phi acting from the Cartesian product of E times E S times, one has this equality. P is a composition of this multilinear operator and the diagonal operator. Diagonal operator is defined here. And if we rewrite this equality with argument, then we can write that P of x is equal to phi xxx. Here phi is called generating for polynomial P, and in the case when it is symmetric, it is unique for polynomial and is called associated for polynomial. So each polynomial has unique associated multilinear operator, and it is denoted by P check. By the way, when I say multilinear, this means that the operator is linear in each variable separately. Let us now say that E and F are Banach spaces, and let me denote by this symbol P. I do not say the other symbols P, let it be P. Let it stand for the space of all norm-bounded, which means continuous as homogeneous polynomials P acting from between these Banach lattices, and it is equipped with the norm which is similar with the linear case. Polynomials from infinite dimensional, from infinite number of variables, or polynomials over infinite dimensional spaces appeared at the end of 19th century, and the very beginning their study was associated with study of infinite dimensional holomorphy, and the relevant historical notes can be found in the book by Dainin, which was published in 1999. In this book, on page 303, Dainin stated the following problem, open question. Is there an infinite dimensional Banach space E with an unconditional basis for which the space of all S homogeneous real-valued polynomials has an unconditional basis? In the same book, he made a conjecture that it is, I'm citing, it's rarely and perhaps never the case that the monomials form an unconditional basis for this space. And let me now explain what meant unconditional, what kind of unconditional basis can be in this space, and what is monomials and monomial expansion. Let me start with the notion of classical notion of Schauder basis. It will be necessary for us, and we'll start with linear case. Let E be a Banach space with a fixed Schauder basis EI. and E prime be the corresponding dual space. Here, as usual, we have what? We have that each element of Banach space has an expansion. You can see it on the second line. X is equal to the sum of x, y, which are reals, and EI. Of course, this is in norm. This is understood in norm. Further on, we can take a functional phi from the dual of E and apply it to X. And I think that these two equalities are quite simple to understand due to the linearity of functional we can take out of the sign of fxi as reals. And further on, we make the following notation. We denote so-called coordinate function x e I prime, which acts as follows. It maps for each x its i's coordinate, and we denote it by here is written how it works, and that's why the second equality in this line is possible. For being now what we get the sum which is expressing the expansion, functional expansion of f we get, and it is fulfilled pointwise. And of course for in the case of Schauder basis, we need a norm that this equality should be fulfilled in norm. That is why it was found out that the functionals, the number of functionals the sequence of functionals ei prime to be a basis in the dual of E, it is necessary to have some more additional condition to on EI. This was the Schauder basis in the in E, and that condition appears to be shrinking, but it is not necessary in my talk what it means. That's why I skip the definition. Now let us talk about bilinear case. We consider two Banach spaces E and F with corresponding fixed Schauder bases En and Fm. Again, we consider, I'll speak with a little bit faster because these are very similar things. We consider again coordinate functionals to EI prime and FI prime, and you can see how they act just the same with the linear case. They maps each x and y to its i's coordinates, and of course we have the expansion of x and y in this way. So for a continuous bilinear form phi acting from the Cartesian product of Banach lattices, we can write these two equalities. Again, due to the bilinearity, this means, again, I will repeat that phi is linear in each coordinate in each variable separately. We can write the first equality, and then again denoting we already denoted coordinate functions, and we can write the second double sum. Here I want to pay your attention to the fact that compared with the linear case, here the situation is the following. This double sum might be not unconditionally convergent, even if En and Fn are separately unconditionally convergent. So in the case when E and F are equal and phi is symmetric, we get a monomial expansion of two homogeneous polynomials. Please remember what the definition I gave at the beginning of my talk. P was a composition of a diagonal operator and a multilinear operator. Here we talk about two homogeneous polynomials. That's why our diagonal operator is denoted by delta 2. And these are some notations. We denote by A, I, E the coefficients and by primes ej prime and ej2 prime, we denote the bilinear operator, which acts as it is shown in 1, 2, 3, third bullet. And by the way, this bilinear operator is called monomial, and this is why we talk about monomial expansion. So, in general case, multilinear case, the situation is quite similar. Again, we consider multilinear operator phi, and again we apply to the expansions of x1, xs. And we get the representation, the expansion, which you can see on the slide. And we call we say that phi is an unconditional multilinear form if the above expansion converges unconditionally for all x's. Unconditionally means that with any permutation of indexes, the convergence remains. So is phi is symmetric? Again, I talk about polynomial. If phi is symmetric, then we have this monomial expansion. The last bullet shows all the notations. I will not stop on them, but in any case, I just want to focus your attention on that. Here we obtained a polynomial, S-homogeneous polynomial with the monomial expansion. The last guy, E prime J1. That's on E prime JS is monomial. So we now understand what we are talking about. And due to the symmetry of multilinear operator phi, it implies that the coefficients in the above expression are symmetric in the sense that whatever permutation we take, again, the result stays the same. And collecting all these coefficients together, we get a representation. We get an unconditional polynomial with monomial expansion. Here we just say about the notations. These are the notations. And so the Dainin's question now can be reformulated due to this understanding of problem of what is monomial expansion. We can reformulate the Dainin's question in the following way. Can the above expansion be unconditionally convergent in infinite dimensional space? And you know, as it turned out, in infinite dimensional case, it was not possible. And the following theorem gives us the answer. It was obtained by Defant and Kelton in 2005, and it says that the Banach space of all S-homogeneous real-valued polynomials on Banach space with unconditional basis has itself unconditional basis if and only if E is finite dimensional. This was an interesting answer, which was obtained, I will repeat, in 2005 by these mathematicians and published in this journal. So, another step in the investigation of Dainin's problem was done by Grecu and Rian. They first introduced the subspace they noted it by P nu, and it is the subspace of all unconditional S-homogeneous real-valued polynomials for which unconditional expansion is unconditionally convergent, and for which the monomial, expansion is unconditionally convergent at every point. They introduced this subject in 2005, and using this notation, now they defined Kelton's theorem can be rewritten in symbols. This means that these two spaces are not equal. It's just in symbols what we told before. And these mathematicians, they raised a problem. And it was to describe the space of all unconditional S-homogeneous polynomials. it's turned out that at this moment the notion of Banach lattices entered. I will give the definition a little bit later in a few moments, but first about the structure of this space. Every Banach space with an unconditional basis is a Banach lattice with order relation, and this order relation is which is defined as follows. This means that an element x is greater or equal to 0, or in vector lattices one used to say positive, if its coefficients x, k are all greater than are positive. And one more notation, we denote by almost the same symbol, but with letter R, the space of, again, as homogeneous real-valued polynomials, but which are regular. Regularity here is the meaning of regularity is the following. The polynomial is called regular if it is representable as the difference of two positive polynomials. And positivity here is understood relative to the structure, to the natural structure of Banach lattice with basis. Using this notation, we can formulate the theorem by Greco-Rian, which was also obtained in the same paper, and it says the following: that the space of that each S-homogeneous real-valued polynomial, which is defined on Banach space with unconditional monomial, unconditional basis, admits a representation via monomials in monomial series, which is unconditionally convergent if and only if it is regular. First, for the first time, polynomials in Banach lattices appeared in the paper by Greco and Rian, and despite the fact that algebraic and the linear topological study of polynomials has a long history, the study of properties of polynomials that depend on the interaction between the order relation and norm relation began only recently. And now it is very important to emphasize that the notions of Banach lattice or regularity or positivity, they arose in the problem which in the solving of problem, the initial formulation of which has nothing common with positivity, with vector lattices. So from this point on, there is an increasing interest in order properties of homogeneous polynomials or just polynomials. As far as I know, to the present moment, there are 3 defended PhD theses on this subject. Chronologically, they were defended in 2007, 2009, 2013, and there is a very serious survey paper which was published in Journal of Mathematical Analysis and Application in 2020. And as we are talking about vector lattices, about order, about Banach lattices, let me very quickly define what I'm talking about. Okay, a real vector space equipped with an order relation is said to be a vector lattice if this order is comparative with the structure of a vector space, in the sense that inequalities can be added and multiplied by positives. And the fact that this is a vector lattice means that for each two elements there exists supremum and infimum. Here are several definitions which we will need. Let me just focus on the last one of them. We say that a set in a vector lattice is order bounded if it is contained in order interval, and the definition of the order interval you can see on the slide. AB is an order interval and defined as follows. Banach lattices. A Banach lattice is a real Banach space E that is simultaneously vector lattice, and also and the order relation is connected with the norm, with the condition of monotonicity. And to provide the examples of Banach lattices, let me say that all classical Banach spaces with corresponding norms and corresponding orders are Banach lattices. And you see the order in these spaces is introduced point-wise if we talk about function spaces, and coordinate-wise if we talk about sequence spaces. And one more remark, I would suggest to keep in mind, always keep in mind when I say Banach lattice or vector lattice, a model example of Banach lattice, which is just to illustrate. It is easy to understand all the terms in this. When we say that Banach lattice can be just each function space, and when we keep in mind this, we can easily, for example, explain the definition of disjoint elements too. You can see the definition on the slide. It is the straight definition, but if we talk about functions, if x and y are functions, then we say that two functions are disjoint if their supports do not intersect, or the intersection of their supports is negligible. But saying support, I mean the space where the function is not equal to 0. And also I want to introduce several classes of homogeneous polynomials. Here E and F are Banach lattices, and the homogeneous polynomial is called orthogonally additive if and only if the additivity equation is fulfilled for disjoint elements. It is bounded in a general sense if the norm is finite. It is order bounded if it carries each order bounded set from E into bounded set in F. It is positive if it's associated. You remember when I first defined polynomials, I said that with each polynomial there is connected multilinear symmetric unique map function which is called associated. So polynomial is called positive, and in symbols it means the following: if it's associated multilinear symmetric operator is positive, and regular, we already discussed this, polynomial is called regular if it is representable as a difference of two positive polynomials. Okay, now I want to present several results which are the motivation of the further investigation. Homogeneous polynomials in vector lattices also appeared previously, but did not attract much attention. And apparently orthogonally additive polynomials in LP spaces were first investigated by Sanderson in 1991, and he obtained the following result. He found out that a polynomial which is defined on LP space as homogeneous orthogonally additive polynomial admits an integral representation, which you can see on the slide, and it can be rewritten in the following way. And what this means? This means that such kind of polynomial can be represented as a composition of a linear bounded functional with the power function. So this phenomenon was called linearization, and it turned out that during several years, mathematicians all over the world tried to find the most general form of this linearization. For example, in 2005 and 2006, there was proved just the same analogous theorem, but in the case when this polynomial P, orthogonally additive polynomial X from CQ. I don't go into details, I just say that the result was just the same. This polynomial defined on the other space was represented as a composition of a linear bounded operator and power function. Then also it was proved in the case when E is functional Banach space and Y is Banach space or Banach lattice. The same result of linearization was obtained. Here it was done in 2006. Also, in similar results in various situations were obtained in 2011, 2012. Until in 2011, there was found the most general case of this theorem. I will not go into the details, but I will say that each orthogonally additive is as homogeneous polynomial admits a representation, acting between vector lattices admits the following representation: a composition of a linear bounded operator and exponential-like function, which is denoted by S or dot. Why exponential-like function? The point is that in arbitrary vector lattice there do not exist multiplication, and that's why the greatest difficulty in this theorem was to not to define, it was already defined, the power of a vector lattice, but to use it. So again, if we talk about model examples of vector lattices, let us think that this is the multiplication in function space. Or also one can say that from the theory of vector lattices, it is a well-known fact that each vector lattice can be extended to a larger vector lattice which admits multiplication, and it is called uniformly complete vector lattice. And here the multiplication and the power can be understood in that way. So next, I want to stop on the analytical description of a class of homogeneous polynomials. This is the class of disjointness preserving operators, disjointness preserving polynomials. I will try to say very quickly what we mean. Let me start with linear operator. Linear operator is called disjointness preserving if we can see the straight definition on the slide, and this means that if the subparts of two functions do not intersect, then the subparts of images of these functions do not intersect. But to understand it more clear, it is enough to know this example, which was obtained by Arendt. So disjointness preserving operator is exactly this one is called weighted shift operator, which means that you have two objects, a continuous map phi and a continuous function a, and you can see that here is first of all a continuous chain, and then we multiply it by continuous function, and this one is exactly disjointness preserving linear operator. The same we can say about multilinear operators, but the definition is the following, that it's gonna be disjointness preserving in each variable separately. And in 2019 it was proved that that each disjointness preserving multilinear operator can be represented as a product of disjointness preserving linear operators, and combined with the Arendt result, together this gives us that a disjointness preserving multilinear operator is exactly this product which is written in the slide. And finally, as homogeneous polynomial is called disjointness preserving if its associated multilinear operator is disjointness preserving. And in 2016, another representation theorem was approved. You can see that it differs from the theorem of 2011 because here we first apply a linear operator and only then we use the power function, and this was the difference. And also here we talk about disjointness preserving homogeneous polynomials, not its smaller class, not about orthogonally additive polynomials. And as a corollary, again, we get together with the Arendt example this representation. This means that disjointness preserving polynomials is exactly the one which is representable as this. Okay, and how much time do I have? Oh, okay. Then I will skip these results during. So there are also many significant. I think so. Interesting results obtained during these years. There was solved several interesting problems about the structure of homogeneous polynomials, and that's on. I do not read them. You can see everything on the slide. And to the most recent results, I want to. As one of the most recent results, I want to say about this result, which is about sums of powers of orthogonally additive polynomials. It's gonna be, I hope, published in 2022. It's very fresh result, and it is about the following. In 2021, three mathematicians, Boydrian and Snegiryova, obtained the following result. They observed positive integers n capital and n with n capital less than n, non-zero scalars lambda 1 and lambda n, and they say that given pairwise independent linear continuous functionals phi 1, phi n capital on a Banach space E, the polynomial which has the following representation. You can see that here we take the sum of each continuous functional each raised to the power of n and multiplied by lambda. So this representable polynomial is orthogonally additive if and only if phi j is disjointness preserving. It was first published online in 2021 and published in 2022. I just don't remember the correct pages. So it was proved that this result is fulfilled in the more general case. I will skip this all and show what before showing, I just want to say that this result remains true when we replace linear continuous functionals by regular operators or even by orthogonally additive polynomials acting between vector lattices, and trying to extend this result to polynomials with values in vector lattices. The main difficulty arose that it was necessary to choose an appropriate substitute of linear independence. And this is the same what I said, and we've got the following theorem. It is the general case of the original theorem of previous authors, and the corollary, which where we get the expansion very similar to Arendt representation of disjointness preserving polynomial. Thank you for attention. questions? This means that it was very clear or unclear.
Can you just maybe comment how it all looks from the point of view of invading of the space of homogeneous polynomials into the tensor forms?
It cannot be explained in 2 words, unfortunately. It's another interesting problem, but in 2 words, I'm sorry, I cannot explain it. Yeah, thank you for your question. Because tensor product is a little bit another.
Any other questions?
I understand this kind of general theory, right?
Yeah.
But if, for example, if you consider a function of several complex variables, you can write expression in series of homogeneous polynomials.
If we work in complex.
Several complex variables. You can express a function as a series of homogeneous polynomials. You can have homogeneous expansion. Represent the function as homogeneous polynomials, right?
Yeah.
So do you have any particular application for more specific cases? This type of case?
You see, what if I understood your question correct, then the stuff about monomial representation and that one, it is the stuff I'm not involved in. I just presented it to show you where from polynomials arise in this definition.
The general theories
Yeah.
direct application.
Yeah.
Okay, let's thank Zalina once again.
Thank you.